Imagine staring into the depths of space and seeing a world not of rock or fire, but of ice, a frozen realm hiding secrets far beyond our wildest dreams. Europa, one of Jupiter's moons, glimmers in the darkness, its surface a mosaic of cracks and ridges stretching across a shell of ice many miles thick. For decades, we've looked at this distant moon and wondered what lies beneath that frozen crust. Could there be an ocean hidden below, vast and dark, holding the ingredients for life? It's a question that has captivated scientists and dreamers alike, and today we're on the verge of an answer that could change everything we know about life in the universe. What if I told you that Europa's ice crust might not be the impenetrable barrier we once thought? New discoveries suggest that this icy shell could be cracking open, creating pathways between the surface and the ocean below. These fractures aren't just random, they might be the key to one of humanity's greatest quests, the search for extraterrestrial life. Think about what that means, a world where geothermal forces or tidal flexing from Jupiter's immense gravity are actively reshaping the landscape, potentially bringing nutrients, heat, and even glimpses of the hidden ocean to the surface. This isn't science fiction, it's the frontier of exploration where rovers, orbiters, and future missions are designed to uncover these very secrets. As we dive into this topic, we'll explore how these cracks form, what they might reveal, and why this phenomenon places Europa at the top of the list for finding life beyond Earth. You're about to embark on a journey to one of the most fascinating places in our solar system, a place where the boundaries between the known and the unknown begin to blur. From the cutting-edge technology enabling these discoveries to the profound implications for our understanding of life itself, this video will guide you through a story of curiosity, innovation, and cosmic wonder. So settle in, open your mind, and let's explore together how Europa's ice crust cracking open could be the breakthrough we've been waiting for. Beneath that fractured, icy shell lies not a void, but a world of liquid water, a hidden ocean of staggering proportions. To truly grasp its scale, picture this. While Earth's deepest ocean trench plunges nearly 7 miles down, Europa's subsurface sea is estimated to be between 40 and 100 miles deep. This isn't a mere layer of slush or a localized pocket. It is a global ocean enveloping the entire moon, trapped between the rocky core and the icy crust. And its volume is almost incomprehensible. Scientists calculate that this single alien ocean holds more than twice the amount of water found in all of Earth's oceans combined. Every sea, every ocean, every drop of water on our planet multiplied by 2, and it's all contained within this one distant moon. But what makes this vast reservoir so compelling isn't just its immense size, it's what's in the water. Data from telescopes and spacecraft like Galileo suggest it's not pure water, but a complex brine, rich in salts like magnesium sulfate and possibly sodium chloride, common table salt. This saltiness is a critical clue. On Earth, salt water doesn't freeze as easily as fresh water, which helps keep this subsurface ocean liquid despite the frigid temperatures at the surface. More importantly, these dissolved minerals are essential nutrients, the kind of chemical building blocks that could potentially support biological processes. The existence of this ocean and its likely longevity spanning billions of years points to another fascinating possibility: hydrothermal vents on the ocean floor. Europa's rocky interior is thought to be geologically active, heated and kneaded by the intense gravitational tug of war with Jupiter and its other moons. This constant flexing generates internal heat, which could power volcanic activity on the seafloor, much like the hydrothermal vents found in the deepest, darkest parts of Earth's oceans. Around these vents on Earth, in complete absence of sunlight, thriving ecosystems exist. They derive energy not from photosynthesis, but from chemosynthesis using chemicals from the vent fluids. If life can flourish in such extreme, isolated environments on our planet, then the conditions on Europa, with a vast, ancient, salty ocean and a likely energy source, present one of the most promising habitats for life we have ever discovered beyond Earth. This isn't just a puddle, it's a potentially living, breathing world buried in the dark. This immense shell of ice, stretching 10 to 15 miles deep in most places, presents a fascinating duality. It is both a formidable barrier and a vital protector, a frozen vault that has shaped Europa's story for eons. On one hand, this crust is our first and greatest obstacle. It's a depth that makes Earth's polar ice cap seem wafer-thin by comparison, a physical blockade separating our robotic explorers from the tantalizing ocean below. Yet, this same icy armor is perhaps the only reason that ocean still exists. Europa orbits within the ferocious grip of Jupiter's radiation belts, a constant storm of high-energy particles that would sterilize any unprotected surface. The ice shell absorbs this brutal onslaught, shielding the delicate aquatic environment beneath from being fried into nothingness. It's a cosmic shield, allowing a potentially habitable world to persist just beneath a surface that is utterly lethal. But the ice isn't just a static block, it's a dynamic geological tapestry. The chaotic terrain of ridges, fractures, and jumbled blocks we see from orbit isn't random chaos. It is a historical record, a frozen archive of Europa's past. Each crack tells a story of immense gravitational stresses, of the moon being stretched and squeezed by Jupiter's pull. These forces generate enough internal heat to keep the ocean liquid and even cause parts of the ice shell itself to soften and churn. Scientists believe this process, called subsumption, might slowly recycle surface material downward over millions of years. This means that compounds from the surface, perhaps even chemical building blocks delivered by comet impacts, could eventually be carried into the ocean below, serving as potential nutrients for any life forms. This concept transforms our view of the ice from a simple wall into a possible conveyor belt. Those dramatic cracks and grooves aren't merely surface features, they might be the very pathways that connect the two worlds. If internal heat or tidal forces causes the ice to thin and fracture all the way down, it could create conduits for water from the deep ocean to well up, freeze, and form new terrain on the surface. In doing so, it might also bring material from the ocean up to where we can sample it. This means a future lander might not need to drill through miles of ice. It might simply need to land near a fresh-looking fracture line and analyze the newly erupted material to get a taste of the hidden sea. The crust is no longer just a barrier to be broken. It is a message to be decoded, and its cracks are the most important lines we will ever read. The very idea of a world with its own moving, shifting tectonic plates was once thought to be unique to Earth. But Europa forces us to expand that definition. We are witnessing tectonics on an ice world, a geological ballet where the dancers are vast plates of frozen water. This isn't rock grinding against rock in slow motion. It's a colder, more brittle, yet eerily familiar process. The surface of Europa is not a single, unbroken shell. Instead, it is fractured into dozens of mobile plates, some spanning hundreds of miles across. These colossal sheets of ice are in constant, albeit slow, motion, jostling against one another, pulling apart, and even diving beneath each other in a process we call subduction. To understand this alien phenomenon, we can look to our own planet's polar regions. In the Arctic Ocean, large sheets of sea ice collide, their edges crumpling upward to form pressure ridges, jagged lines of broken ice that can tower several meters high. On a much grander scale, this is precisely what we see on Europa, but the ridges there can be hundreds of meters tall and stretch for thousands of miles, crisscrossing the landscape like the seams on a global baseball. Another powerful earthly analog is found where glaciers meet the ocean. In Greenland and Antarctica, ice shelves, massive extensions of glaciers floating on the sea, are constantly cracking, calving off icebergs and slowly flowing. They are dynamic systems, not static ice. Europa's crust behaves in a similar way, but as a global system, with its ocean being the liquid water below and its glaciers being the entire icy lithosphere. The engine powering this incredible activity is the immense gravitational pull of Jupiter. As Europa orbits the gas giant, it doesn't follow a perfect circular path. Its orbit is slightly elliptical, meaning its distance from Jupiter changes. This variation subjects the Moon to a relentless tidal tug of war. Jupiter's gravity pulls harder on the side of Europa closest to it, then relaxes its grip as the Moon rotates. This constant flexing generates enormous internal friction and heat, which keeps the subsurface ocean liquid and also causes the ice shell itself to become warm and pliable in its deeper layers. This allows the ice to convect, with warmer, less dense ice slowly rising from the bottom of the shell while colder, denser ice at the surface sinks. This convective churning, combined with the direct tidal stress, provides the powerful forces that drive the ice plates apart, push them together, and ultimately recycle them. This is where we see the most striking parallel to Earth: subduction. On our world, dense oceanic crust sinks beneath lighter continental crust, diving back into the mantle. On Europa, some ice plates appear to be doing the very same thing. Scientists analyzing images from spacecraft have identified areas where one plate seems to have been overridden by another, with the underlying plate bending downward and disappearing from the surface. This process would explain certain mysterious features like disappearing gaps in the terrain. If a plate is subducted, it doesn't just vanish. It likely gets warmed by the internal heat, melts, and its material is eventually recycled, perhaps even emerging again at a different fracture where new ice is forming. This continuous cycle of destruction and renewal means that Europa's surface is relatively young, geologically speaking, constantly being repaved and rewritten by the restless activity beneath. It's a living, breathing world of ice, and its tectonic story is the key to unlocking the secrets it holds within. The relentless grinding and flexing of Europa's icy shell doesn't just create cracks and moving plates, it also builds pressure, and that pressure must find a way to escape. This leads us to one of the most visually spectacular and scientifically vital processes on the Moon: cryovolcanism. Forget the iconic image of a volcano spewing fiery, molten rock. On this frozen world, volcanoes erupt with water and slush. Think of it as a geyser, but on a planetary scale and in deep freeze. These are not mere water features, they are potentially the most direct pipelines between the hidden ocean and our waiting robots. The mechanics behind these ice volcanoes are both familiar and utterly alien. Deep within Europa's ice shell, the heat from tidal flexing and radioactivity can melt pockets of ice, creating vast chambers of liquid water or a warmer, softer slush. This material, trapped under the immense pressure of the overlying ice, seeks any weakness in the crust above. When a tectonic fracture provides a pathway, this buried reservoir explosively decompresses, forcing its way upward and erupting onto the surface in a brilliant, freezing plume. The material doesn't erupt as a scorching liquid. It instantly flash freezes in the vacuum of space and the Moon's surface temperatures nearing -260 degrees Fahrenheit. What lands on the surface isn't lava rock, but a fine snow or a crystalline frost, potentially coating the landscape around the vent for miles. This process transforms our entire strategy for searching for life. Instead of the monumental engineering challenge of drilling through 10 miles of solid ice, a spacecraft could simply fly through one of these plumes or land near a vent and sample the freshly deposited material. We are, in effect, being handed a free sample of the deep ocean delivered directly to the surface. The implications are staggering. If the ocean below contains the chemical building blocks of life, or even living microorganisms themselves, those biosignatures could be frozen within this erupted material. A lander's robotic arm could scoop up this icy spray and, for the first time in history, analyze the components of an alien ocean without ever getting its feet wet. The potential for nutrient transport is equally profound. On Earth, volcanic eruptions recycle minerals and gases from the deep mantle, enriching the surface and atmosphere. Europa's cryovolcanoes could be performing a similar function for biology. If hydrothermal vents on the ocean floor are indeed creating a rich soup of organic compounds, an eruption could carry those nutrients upward, seeding the base of the ice shell or even the surface. This could create habitable niches within the ice itself, where microbes might thrive in tiny pockets of liquid water, sustained by chemicals from both above and below. A single eruption could therefore do more than just connect two environments. It could actively mix them, fostering life in places we never thought to look, and then offering us a frozen record of that activity to study. It is a natural elevator between the abyss and the stars, and it might just be our ticket to discovering we are not alone. Among the most telling landscapes on Europa are the vast stretches known as chaos terrain. These are not the orderly ridges and fractures we see elsewhere. They are zones of pure geological anarchy. Picture a massive pane of glass that has been shattered by a tremendous impact, its pieces then haphazardly frozen back together in a completely new, disordered arrangement. That is the essence of chaos terrain, a jumbled, broken region of ice blocks, some as large as cities, set in a matrix of smoother, younger ice. This isn't the slow, predictable grinding of tectonic plates. This is evidence of a catastrophic disruption from below, a place where the very foundation of the icy shell has been utterly overturned. The prevailing theory for how these bizarre features form is as dramatic as they look. Scientists believe that vast reservoirs of relatively warm, liquid water become trapped within the ice shell itself, perhaps warmed by tidal energy or by upwelling from the ocean far below. Over time, this lake-sized lens of liquid water begins to melt the icy ceiling above it, weakening the entire structural integrity of that entire section of the crust. Eventually, the weight of the ice on top of this liquid pocket becomes too much for the weakened walls to bear. The entire ceiling collapses in a spectacular event, sending huge icebergs tumbling and rotating into the slushy water below. Then, in the extreme cold of the surface, this chaotic mixture of ice and water rapidly refreezes, locking this incredible disruption in place for eternity. What makes chaos terrain so incredibly exciting is that it acts as a direct historical record of a direct interaction with the subsurface ocean. The material that flooded upward during that collapse event came from deep within the ice shell and likely carried with it chemicals and compounds from the ocean itself. When it refroze, it preserved that sample perfectly. This means that by studying the composition of the ice within these chaos regions, a future lander could effectively perform a chemical analysis of the deep ocean without drilling an inch. Areas like Connemara Chaos, one of the most famous and well-studied examples, are not just geological curiosities. They are nature's own sampling sites pre-prepared for our exploration. The presence of such extensive chaos terrain also tells us that Europa is far from a dead, frozen world. These features are, geologically speaking, quite young. Their crisp, sharp edges and lack of heavy cratering suggest they formed recently, and that this process of disruption and renewal is ongoing. This paints a picture of a dynamic world where the ocean doesn't just sit passively beneath a static lid. It is an active participant in shaping the surface, occasionally reaching up with tremendous force to break apart the frozen sky and remind us that there is a warm, liquid heart beating within this distant, icy moon. It is in these chaotic places that the boundary between the surface and the sea is at its thinnest, offering our clearest window into the mysteries hidden below. At the heart of this entire cosmic drama is a simple, powerful force, gravity. Jupiter, the solar system's behemoth, doesn't just anchor its family of moons in orbit. it actively shapes their very existence through its overwhelming gravitational influence. For Europa, this relationship is an intimate and constant dance, one that provides the energy for everything we see. To grasp how this works, we can look to our own planet. Earth's oceans experience tides because the Moon's gravity pulls more strongly on the side of Earth facing it, creating a bulge of water. The Sun exerts a smaller, similar effect. As Earth rotates, these bulges move around the globe, causing the familiar rise and fall of sea levels. Now amplify that concept to an almost unimaginable degree. Europa is locked in an orbital embrace with the most massive planet in our solar system. Furthermore, its orbit is not a perfect circle, it's slightly elliptical. This small difference is everything. As Europa travels along this oval path, its distance from Jupiter constantly changes. When it swings closer to the giant planet, Jupiter's gravitational pull is immensely stronger, stretching the Moon toward it. As Europa moves to the farthest point in its orbit, that grip relaxes, and the Moon is allowed to settle back into a more spherical shape. This perpetual, rhythmic stretching and relaxing is what we call tidal flexing. But this isn't just a surface-level phenomenon. This flexing occurs through the Moon's entire structure, its rocky metal core, its global ocean, and its thick icy shell. All of these materials have internal friction. They resist being deformed. As Jupiter's gravity relentlessly kneads Europa like dough, this internal friction generates an enormous amount of heat deep within the Moon's interior. It is this heat, born from gravitational stress, that acts as Europa's hidden engine. It prevents the global ocean from freezing solid into a block of ice, despite the Moon's vast distance from the Sun. This process turns what should be a frozen, inert world into a geologically active one. The effects of this tidal heating are most dramatically visible on the ice shell itself. The crust is not a flexible, uniform material. It is rigid and brittle. As the Moon's interior is stretched and compressed, immense stress builds up in this frozen outer layer. These stresses far exceed the strength of the ice, and the only way to relieve the pressure is for the crust to fracture. This is the primary driver behind the vast network of cracks, ridges, and bands that scar Europa's surface. Each line is a testament to a breaking point, a moment when the ice could no longer withstand the forces exerted by Jupiter's relentless tug. This dynamic also explains why the surface appears so young and freshly repaved. The constant geological activity driven by tidal forces ensures that old, cratered terrain is continuously broken apart, subsumed, or covered by new material erupting from below. Without this internal engine powered by Jupiter, Europa would be a cold, dead, and heavily cratered ice ball. Instead, it is a world teeming with potential, its warm heart beating to the rhythm of a giant's gravity, its frozen skin cracking open to reveal the vibrant possibilities hidden within. Deep beneath the perpetual ice, at the very bottom of this alien sea, lies what might be the most promising environment for life in the entire solar system. Here, in the absolute darkness and under crushing pressure, Europa's rocky core is likely home to a network of hydrothermal vents, much like those found in the deepest trenches of Earth's oceans. These are not simple cracks, they are powerful, mineral-rich geysers superheating the surrounding water, and they could be the very cradles that nurture life in an otherwise sunless abyss. To understand why these features are so compelling, we need to journey to our own planet's most extreme environment, the deep sea vent systems. At the bottom of the Atlantic and Pacific Oceans, far beyond the reach of any sunlight, exist towering chimneys of mineral deposits billowing out water darkened by dissolved metals and superheated to temperatures that could melt lead. For decades, we assumed these volcanic plumes were barren, geological curiosities. Then, in 1977, the submersible Alvin made a discovery that shook biology to its core. These vents were not desolate, they were oases teeming with bizarre and abundant life. Giant tube worms, blind shrimp, strange crabs, and unique species of mollusks thrived in these superheated, chemical-rich waters, forming dense, complex ecosystems entirely cut off from the sun's energy. This revelation forced a complete rewrite of the rules for life. These creatures do not rely on photosynthesis, the process that powers almost every other ecosystem on Earth's surface. Instead, they rely on chemosynthesis. Specialized bacteria form the base of this entire food web. They possess the incredible ability to harness the chemical energy stored in the toxic compounds spewing from the vents, primarily hydrogen sulfide. These microbes convert this inorganic chemical soup into organic matter, essentially creating food from poison. The larger animals then either consume the bacteria directly or live in symbiosis with them, hosting the microbes inside their bodies to provide a constant supply of nutrients. Life here has found a way to flourish without a single photon of sunlight, powered solely by the geothermal heartbeat of the planet itself. This is the powerful analogy that fuels excitement for Europa. The conditions around its hypothetical vents are almost certainly similar and could even be more favorable. Jupiter's gravitational tug keeps Europa's core warm and geologically active, likely creating a vast network of these vents on the ocean floor. The water circulating through the hot rocks would leach out a rich cocktail of minerals and chemical compounds, not just sulfides, but perhaps also vital elements like carbon, nitrogen, phosphorus, and potassium. This process would provide both the necessary energy and the fundamental building blocks for life to arise and persist. Furthermore, Europa's ocean offers one crucial advantage over Earth's: time and stability. On our planet, individual vent fields are ephemeral. They become active for a few decades or centuries and then go dormant as geological activity shifts, dooming the ecosystems that depend on them. Europa's ocean, however, has likely existed for billions of years, and the tidal heating that powers its vents is constant and global. This means a stable, long-term energy source could have allowed life not only to emerge but to evolve and potentially diversify over an unimaginable timescale. We might not find simple microbes. We could discover complex, sophisticated organisms that have perfected a way of life in the eternal dark. A hydrothermal vent on Europa isn't just a niche. It is a potential metropolis, a proof that where there is energy, water, and the right chemistry, life can find a way, no matter how far from the light of a star. Now, while hydrothermal vents offer a compelling energy source in the depths, there is another, more surprising power source at work much closer to the surface, one born from the very radiation that makes Europa's exterior so deadly. This process is called radiolysis, and it turns a destructive force into a potential engine for life. High above Europa, Jupiter's immense magnetic field whips charged particles to nearly the speed of light, creating a brutal and continuous radiation bath that bombards the Moon's icy surface. This isn't a gentle shower, it's a torrential downpour of energy that would be instantly lethal to any known life form. But when these high-energy particles slam into the ice, they don't just sterilize it, they fundamentally change its chemistry in a way that could benefit life far below. The heart of this process is remarkably straightforward yet incredibly powerful. As these radiation particles, primarily electrons and ions, rip through the water ice, they smash into the water molecules themselves. A water molecule, H2O, is made of two hydrogen atoms bonded to one oxygen atom. The immense energy from the impact is enough to shatter these molecular bonds, blasting the water apart into its component pieces. What's left behind isn't just random debris, it's a soup of highly reactive fragments called radicals. This includes free hydrogen gas, which is very light and often escapes into space, and most importantly, highly reactive oxygen compounds like hydrogen peroxide and molecular oxygen. These oxygen-rich molecules are known as oxidants, and they are bursting with stored chemical energy, eager to react with anything that can provide a fuel source. This is where the dynamic geology of Europa's ice shell becomes absolutely critical. We've already discussed how the crust is churning, with convection currents slowly dragging surface material downward over geological timescales through subduction or other processes. This means that ice laden with these energy-rich oxidants created by radiation at the surface could be slowly transported deep into the shell and eventually delivered right to the interface with the liquid ocean. Imagine it as a slow, geological conveyor belt, patiently carrying packages of chemical energy from the lethal surface down into the protected depths. Once these oxidants reach the ocean, they could meet their perfect partner, reductants. These are chemicals that readily give up electrons, acting as the fuel. On Earth, in a process we call redox chemistry, the reaction between an oxidant and a reductant releases energy. This is the fundamental principle behind how we burn fuels, and it's also how our own cells power themselves. On Europa, the reductants could be minerals like sulfides or iron compounds leaching out of the rocky seafloor from those very hydrothermal vents we discussed. When an oxidant from the surface meets a reductant from the depths, that reaction releases energy that a hypothetical microbe could harness through its metabolism. This creates a breathtakingly elegant and self-sustaining system. The radiation that bombards the surface, which we once saw only as a barrier, is actually a key part of the Moon's energy cycle. It manufactures a vital ingredient for life upstairs, and Europa's own geological activity provides the delivery service to bring it downstairs. This means that life in Europa's ocean might not be solely dependent on the heat from hydrothermal vents. It could also thrive in the darkness of the water column or even within the ice shell itself, sustained by this constant drizzle of chemical energy from above. It suggests that Europa isn't just providing a habitat, it's providing a full menu of power options, making the possibility of life there not just a hopeful guess, but a robust scientific prediction. So how do we peer through miles of solid ice to map this hidden world? The key lies in a technology that turns radar from a simple detection tool into a powerful geological telescope. Ice-penetrating radar doesn't rely on visible light. Instead, it sends out pulses of long-wavelength radio energy that can travel through solid ice with astonishing clarity. Think of it like a medical ultrasound for a planet. Just as high-frequency sound waves can create an image of a baby in the womb by bouncing off different tissues, radar waves sent from an orbiting spacecraft can penetrate Europa's frozen crust and reflect back from hidden boundaries deep below. The time it takes for that signal to return reveals the depth of the feature, while the strength of the reflection tells us about its composition. A strong, bright return likely means a sharp transition, like the boundary between solid ice and liquid water, while softer, fainter returns might show layers of different ice types or pockets of slush. This isn't just theoretical. We've perfected this technology right here on Earth. For decades, scientists have used ice-penetrating radar to map the bedrock hidden beneath the ice sheets of Greenland and Antarctica. Aircraft flying over these frozen landscapes send radar pulses downward, meticulously charting subglacial mountains, valleys, and even entire lakes buried for millions of years. The discovery of Lake Vostok, a vast liquid water body under 2.5 miles of Antarctic ice, was a triumph for this very method. It proved that radar could not only find liquid water under immense ice, but also map the intricate structures surrounding it. This gives us tremendous confidence that the same principles will work at Europa, albeit on a grander and more complex scale. Future missions like the European Space Agency's Jupiter Icy Moons Explorer, JUICE, and NASA Europa Clipper are equipped with advanced versions of this technology. As these spacecraft make dozens of close flybys of Europa, their radar instruments will fire pulses at the surface. By meticulously assembling these individual soundings, scientists will create a three-dimensional tomographic map of the ice shell, revealing its internal architecture in unprecedented detail. We'll be able to see the sloping layers, the potential water pockets within the ice, and most importantly, identify the precise boundary where solid ice gives way to the global ocean. This data will be revolutionary. It will tell us exactly how thick the ice is in different regions, pointing future landers to the thinnest spots or, even better, directly to those areas where chaos terrain or fractures have brought ocean material within easy reach. The ultimate goal is to find what scientists call a brine lens, a sizable pocket of liquid water trapped within the ice shell itself. These would be the most promising targets for a future lander mission. Instead of facing the near-impossible task of drilling 10 miles down to the ocean, a rover could potentially drill just a few hundred meters into one of these accessible pockets and directly sample liquid water that has been in recent contact with the ocean below. Ice-penetrating radar is the guide that will lead us to these doors. By mapping the unseen, it transforms a mission of blind exploration into a targeted search for life, turning the entire ice shell into a transparent window and giving us our first real look into the anatomy of an alien world. But knowing where to look is only half the battle. We need the right tools for the job. This is where NASA Europa Clipper mission comes in, a spacecraft designed not to land but to perform reconnaissance, acting as our eyes and ears in orbit around this enigmatic moon. Slated for a launch in 2024, Clipper's sole purpose is to determine if Europa possesses the three key ingredients for life: liquid water, essential chemical elements, and sufficient sources of energy. It is, in essence, a habitability detective, and its suite of 9 powerful instruments is its detective's kit, each one designed to answer a specific piece of this grand puzzle. To study the complex ice shell, Clipper carries a powerful radar system, much like the ones we use on Earth. This instrument, called Reason, will send radio waves deep into the crust, mapping its internal structure layer by layer. It will hunt for those hidden brine pockets and water layers within the ice, essentially giving us a 3-dimensional ultrasound of the moon's frozen exterior. By identifying thinner regions, fractures, and potential delivery routes for ocean material, Reason will create a roadmap for future lander missions, pointing them directly to the most promising sites for sampling. Understanding the ocean's composition is equally critical, and for this, Clipper has a magnetometer. This tool measures the strength and direction of magnetic fields. Here's the brilliant part. As Europa orbits Jupiter, it moves through the planet's gigantic magnetic field. If a global, salty ocean is sloshing beneath the ice, it will generate an induced magnetic field in response, one that subtly opposes Jupiter's. By meticulously measuring these tiny magnetic fluctuations, Clipper can not only confirm the ocean's existence beyond any doubt, but also tell us about its salinity and approximate depth. A saltier ocean will conduct electricity better and create a stronger magnetic signal, giving us a remote taste of the sea's chemistry. And then there are the plumes. To catch these fleeting eruptions in the act, Clipper is armed with both a suite of cameras and an ultraviolet spectrograph. The cameras will scour the limb of the moon against the blackness of space, looking for the faint, telltale silhouettes of erupting material. Meanwhile, the spectrograph will analyze the faint glow of ultraviolet light around Europa. If a plume erupts, it will temporarily absorb and scatter specific wavelengths of light, revealing its composition. Is it mostly water vapor? Does it contain simple organic molecules? The spectrograph will give us our first direct chemical analysis of what might be coming from the ocean below. Finally, to directly sample these plumes if it flies through one, Clipper carries a mass spectrometer. This instrument can identify the chemical makeup of any gas or dust particles it encounters, capable of detecting complex organic compounds, the building blocks of life. While Clipper is not a life detection mission itself, its data will tell us if the conditions are right and if the ocean contains the necessary chemistry. It is the crucial first step, the surveyor charting the territory so that one day a lander can follow, drill, and perhaps finally answer the question we've been asking for centuries. For all the incredible potential of orbital mapping, the ultimate prize remains a direct sample of Europa's ocean, and nature may have provided us with a breathtaking shortcut. Instead of engineering a probe to drill through miles of ice, scientists are preparing to simply catch what the moon is already throwing into space. Europa, much like Saturn's moon Enceladus, is believed to episodically erupt in colossal geysers, spewing water vapor and ice particles from its subsurface ocean through fissures in the crust. These plumes are our golden ticket, offering a free sample return mission where we don't even have to land. The concept is as elegant as it is ambitious. A spacecraft like Europa Clipper, during one of its 45 planned close flybys, could adjust its trajectory to pass directly through the faint outer reaches of one of these erupting plumes. In that fleeting moment, measured in seconds, its onboard instruments would have a chance to analyze the plume's composition in situ. The spacecraft wouldn't need to slow down or land. It would be a high-speed snapshot, a momentary dip into the spray of an alien ocean. The key instrument for this task is a mass spectrometer, a sophisticated tool that can identify molecules by weighing them. As ice particles and gas from the plume strike the instrument, it would vaporize them and measure the mass of each resulting fragment, building a detailed inventory of the plume's chemical content. This data could reveal the presence of salts, organic compounds like methane or carbon chains, and even complex prebiotic molecules, all crucial clues about the ocean's habitability. However, hunting these plumes is an exercise in patience and prediction. Unlike the steady, predictable jets on Enceladus, Europa's plumes are elusive and intermittent, making them incredibly difficult to catch in the act. Evidence for their existence comes from tantalizing clues, like observations from the Hubble Space Telescope that detected what appeared to be transient excesses of hydrogen and oxygen, the components of water near Europa's south pole. The challenge for mission planners is to know where and when to look. They will use data from Clipper's cameras and ultraviolet instrument to constantly monitor the moon's limb, watching for the faint glow or darkening that might betray an ongoing eruption. Once a likely candidate is spotted, the team could potentially command the spacecraft to alter its course slightly on a subsequent orbit, steering it toward the potential activity for a closer look. Successfully capturing and analyzing material from a plume would be a monumental achievement. It would effectively bypass the most daunting technological hurdle of ocean exploration. The data returned would tell us not just about the ocean's chemistry, but also about its potential to support life. Finding evidence of complex organic chemistry in these samples would be a powerful indicator that the processes needed for life are actively at work in Europa's dark depths. While it wouldn't constitute direct proof of life itself, it would tell us that we are looking in the right place, transforming Europa from an object of speculation into a confirmed target for a future mission designed to find the answer. But the true future of exploration lies not in flying by, but in touching down. Orbital reconnaissance gives us the map, but to find the treasure, we must go to the surface ourselves. This next leap is the Europa Lander mission, a concept that moves us from being distant observers to active participants in the search. Imagine a robust, nuclear-powered lander, carefully setting down on the fractured, icy plains, its legs sinking slightly into the frost. This wouldn't be a simple rover designed to wander. It would be a dedicated scientific laboratory, parked at the most promising site identified by the Clipper mission with one primary goal: to search for signs of life. The lander's toolkit would be a marvel of miniaturization and precision. Its most crucial instrument would be a drill, designed to penetrate anywhere from a few inches to potentially several feet into the Europan ice. This isn't about reaching the ocean. That remains a task for a far more advanced future. Instead, it's about accessing ice that has been recently altered or emplaced. The ideal landing site would be on a relatively smooth, young patch of terrain next to a prominent crack or a chaos region. Here, material from the subsurface may have been churned up to the surface or deposited by a recent plume fallout, frozen in time just below a thin layer of newer ice. The drill would core out samples and feed them directly into a suite of onboard analyzers. The most important of these would be a gas chromatograph mass spectrometer, a device that can vaporize a tiny ice sample and identify the exact molecular weight of every compound released. This instrument could detect the complex organic molecules like amino acids or lipids that are the fundamental building blocks of life as we know it. But detecting building blocks isn't enough. We need to look for the architects. That's where other instruments come in. A Raman spectrometer would blast the sample with a laser, causing its molecules to vibrate in a unique signature that can distinguish between organic material that is merely present and organic material that has been processed by a biological system. It could potentially see the difference between a random collection of chemicals and the organized structures of a cell membrane. Beyond just analyzing ice, the lander would be equipped with a sophisticated microscope, possibly with fluorescent capabilities. After preparing a sample, it would scan for any physical structures that resemble microorganisms. While we wouldn't expect to find fossilized shells, we might see the faint outlines of cells, their shapes preserved in the ice. To confirm any potential discovery, the mission would likely include a test for chirality. Many key organic molecules used by life on Earth come in two mirror image forms, like a left hand and a right hand. Abiotic chemistry produces a 50-50 mix of both. Biology, however, almost exclusively uses one hand. All amino acids in Earth life are left-handed. If the lander's instruments found an overwhelming abundance of one chiral form over the other in these organic molecules, it would be the most powerful evidence imaginable that a biological process, not just random chemistry, is at work on Europa. This one-way mission would be our first intentional, direct contact with another world's potential biology, a gentle search for a neighbor in the vast and silent cosmic ocean. The quest to understand what might live on Europa doesn't require us to only look outward. Some of the most compelling clues are found in the most hostile corners of our own planet. Here, life doesn't just survive in conditions we once thought impossible, it thrives. These incredible organisms are known as extremophiles, lovers of extremes, and they provide our best, most tangible model for what we might one day find swimming in the dark or frozen within the ice of that distant moon. They are living proof that the recipe for life is far more flexible and resilient than we ever imagined. Consider the perpetually frozen landscape of Antarctica. For centuries, it was seen as a sterile desert, a place where life could barely cling to existence. But beneath the massive ice sheets, we've discovered a hidden world that shatters that notion. Take Lake Vostok, for instance, a body of liquid water buried under 2.5 miles of solid ice, isolated from the rest of the world for millions of years. It is a place of complete darkness under immense pressure and with limited nutrients. Yet, when scientists finally drilled down and sampled the lake's water and the sediment at its bottom, they found a surprising diversity of microbial life. These bacteria don't rely on the sun. They are chemosynthetic, harvesting energy from minerals dissolved in the water or leaching from the bedrock. They've crafted an entire ecosystem in total isolation, a direct parallel to how life could persist in Europa's sunless ocean, cut off from the surface by a crushing ceiling of ice. Then there are the deep ocean trenches like the Mariana Trench, the deepest point on Earth. Here, the pressure is 1,000 times greater than at sea level, a force that would instantly crush most surface creatures. In this crushing, pitch-black environment, we find entire communities flourishing around hydrothermal vents. Giant tube worms, blind shrimp, and unique species of snail all gather around these mineral-rich geysers, sustained by bacteria that perform chemosynthesis. These bacteria convert the toxic, sulfurous compounds billowing from the vents into usable energy, forming the foundation of a food web that operates entirely independently of sunlight. This is not a marginal, struggling existence. It is a vibrant and abundant oasis. The lesson for Europa is profound. If life can find such a robust foothold in the extreme pressure and chemical richness of Earth's seafloor vents, then the hypothesized vents on Europa's ocean floor represent perhaps the single most promising habitat for complex life beyond our planet. But perhaps the most direct analogy for life within Europa's icy crust itself is found closer to the surface, locked within the sea ice of the Arctic. This is not solid, uniform ice. It's a complex matrix riddled with tiny channels and pockets of extremely salty liquid water called brine. Despite the freezing temperatures, the high salt content prevents this water from solidifying, creating a labyrinth of microscopic habitats. Within these tiny, interconnected aquariums, scientists have discovered a whole menagerie of life, from specialized algae and bacteria to more complex single-celled organisms called ciliates. These entire microscopic ecosystems live their entire lives trapped in the ice, sustained by chemical reactions and the slow diffusion of nutrients. They demonstrate that life doesn't need a vast ocean. It can make a home within the ice itself. For Europa, this suggests that the moon's thick crust may not be a barren barrier at all. It could be its own habitat, a Swiss cheese of potential living spaces where microbes could exist in pockets of brine, sustained by the chemical energy delivered from the radiation-processed surface above and the nutrients welling up from the ocean below. These earthly extremophiles teach us a crucial lesson. Life is not defined by our comfortable, sun-drenched standards. It is defined by its breathtaking adaptability. It shows us that the fundamental requirements are liquid water, a source of energy, and the right chemistry, not necessarily a sun. Europa appears to offer all three in abundance. The organisms we might find there could be microbial, similar to the chemosynthetic bacteria in our deep oceans or the hardy microbes in Antarctic lakes. Or, given the stability and vast timescale of Europa's ocean, evolution may have had the opportunity to craft something more complex, perhaps filter-feeding organisms that graze on microbial mats near vents, or even free-swimming creatures that have adapted to the perpetual dark. By studying life at its limits here, we are essentially writing a field guide for what to look for there, turning a question of pure speculation into a structured, scientific search for the familiar in the utterly alien. So if a future lander drills into the ice and collects a sample, what exactly will it be searching for? The answer lies in biosignatures, which are not the aliens of science fiction, but the subtle chemical and structural traces that life leaves behind. The first and most crucial category is complex organic molecules. This goes far beyond just finding simple carbon chains. It's about discovering a specific, telltale distribution of compounds. On Earth, life is built from a standard set of building blocks: amino acids to make proteins, nucleobases for genetic information like DNA and RNA, and lipids for cell membranes. Finding a random, sparse mixture of these molecules could just indicate interesting probiotic chemistry. But discovering a rich, abundant, and specific suite of them, like 20 different types of amino acids alongside nucleobases and fatty acids, would be a deafening hint that biological processes are at work manufacturing these parts in bulk. The most powerful biosignature within this category, however, is a concept called homochirality, or molecular handedness. Many organic molecules exist in two forms that are mirror images of each other, just like your left and right hands. Non-biological chemical processes always produce a 50-50 racemic mixture of both hands. Life, in its exquisite specificity, almost always chooses just one. All amino acids that make up proteins in Earth life are left-handed, while the sugars in our DNA and RNA are right-handed. This preference is a fundamental signature of biology. If an instrument on a lander were to analyze amino acids in a Europan ice sample and find that 90% or more were left-handed, it would be incredibly difficult to explain without invoking life. This molecular preference is so robust that it could persist long after the organisms themselves have died, serving as a fossilized clue to biological activity. Beyond the building blocks, scientists will also look for evidence of metabolism in the form of isotopic ratios. Elements can come in different versions called isotopes, which have the same chemical properties but different atomic weights. Life, because it prefers reactions that are faster and require less energy, often discriminates between these isotopes. For example, biological processes on Earth tend to incorporate the lighter carbon-12 isotope over the heavier carbon-13. This means that organic material produced by life has a distinctly lower ratio of carbon-13 to carbon-12 than inorganic material from a geological source. The same is true for other elements like nitrogen, sulfur, and hydrogen. So if a sample from Europa shows a pronounced skew in these isotopic ratios within its organic compounds, it would be a strong indicator that life was actively processing those elements, effectively leaving its fingerprint on the atomic makeup of the Moon. Finally, the most direct and thrilling evidence would be visual. A microscope on board a lander could be used to search for actual physical structures. We wouldn't be looking for fossilized shells or bones, but for the microscopic shapes of cells themselves. This could include individual microbe-like forms, but even more compelling would be finding communities of cells stuck together in filaments, mats, or chain structures that are commonly formed by bacterial communities on Earth, especially around nutrient sources like hydrothermal vents. To enhance this search, a microscope might use fluorescent dyes that bind specifically to common organic molecules in cell membranes or genetic material, causing any potential cells to literally glow under the laser. Finding a complex, ordered structure that glows in this specific way would be a moment of profound discovery. While no single line of evidence would be conclusive on its own, a combination of complex organics, molecular handedness, skewed isotopic ratios, and physical microstructures would build an overwhelming case that we are not alone, that even in the sunless depths of an alien ocean, life has found a way. For generations, the blueprint for finding alien life has been defined by a single, powerful idea: the habitable zone. This is the region around a star where conditions are just right, not too hot, not too cold for a planet to have liquid water on its surface. It's the so-called Goldilocks zone, and for a long time it was the only place we thought to look. This concept naturally focused our search on planets like our own, orbiting at that perfect, cozy distance from a sun. But what if this entire framework is too narrow? What if we've been looking for life in the wrong places, simply because we were using a map that was missing entire continents of possibility? Europa forces us to redraw that map entirely. This distant, ice-shrouded moon orbits Jupiter 5 times farther from the Sun than Earth does out there. Sunlight is feeble, a mere 25th of the strength we enjoy, and surface temperatures are a brutally cold -260 degrees Fahrenheit. By every traditional measure of the habitable zone, Europa is a frozen wasteland, a place where water can only exist as solid ice. It should be a biological dead end. And yet, as we've discovered, it is one of the most promising places for life we have ever found. This paradox shatters the old definition of habitability. Europa teaches us that it isn't about your distance from a star, it's about your access to energy and liquid water. And a star is not the only source of energy in the universe. The real engine for Europa's potential is not overhead but deep within. The immense gravitational pull of Jupiter provides a constant, relentless source of internal heat through tidal flexing. This means that a world can be far from the warmth of its sun and still be incredibly geologically active, still possess a vast global liquid ocean, simply because it is being gravitationally needed by a giant planet. This revelation expands the cosmic real estate for life by orders of magnitude. Suddenly, we must consider not just planets but their moons as well. In our solar system alone, this new thinking puts Europa, Enceladus, Ganymede, and even distant Triton on the list of potential abodes for life. When you look out at the night sky and consider the countless galaxies, each with billions of stars, you are already contemplating a vast number of possibilities. But now, for every star with planets, you must also consider the moons orbiting those planets. The number of potential habitats in the universe didn't just double, it may have multiplied exponentially. This shift in perspective is as profound as the Copernican revolution that moved Earth from the center of the universe. We are now moving the Sun from the center of the biological universe. We are admitting that life may not need a sunny, Earth-like beach to get started. It might prefer, or even be more common, in the dark, pressurized abysses of ice-covered oceans, warmed from below by the gravitational embrace of a giant. The Goldilocks zone is no longer a narrow band of space around a star. It is any environment, anywhere, where chemistry can become biology. It is a set of conditions, not a specific location. And that changes everything about our place in the cosmos and our search for company within it. This incredible quest to find life, however, comes with a profound and sobering responsibility. The responsibility to ensure that we do not become the very thing we are searching for. The moment we send a spacecraft from Earth to another world, we risk carrying with us an invisible stowaway microbial life from our own planet. These tiny hitchhikers, incredibly resilient bacteria and spores, could potentially survive the journey through space and contaminate the pristine environment of Europa. This isn't a minor technicality, it's a monumental ethical and scientific dilemma known as planetary protection. The core principle is simple yet vital. We must protect other planetary bodies from contamination by Earth life, and we must equally protect Earth from any potential extraterrestrial organisms we might bring back. For Europa, with its potentially habitable ocean, this is arguably the most critical consideration of all. Why is this so crucial? Imagine the horror of a future lander drilling into the ice, its sophisticated instruments detecting what appears to be clear signs of life, only for scientists to realize years later that they were actually analyzing a stubborn Earth microbe that had clung to the spacecraft and survived. This false positive would be a scientific catastrophe, rendering the entire multi-billion-dollar mission meaningless and forever clouding our understanding of Europa's true biology. It would be the ultimate case of cosmic contamination where we inadvertently discover ourselves. Even more troubling is the potential for forward contamination. If an Earth microbe were introduced into Europa's ocean, it could outcompete or fundamentally alter any native life forms before we even have a chance to study them. We would be responsible for irrevocably damaging a unique ecosystem that has been evolving in isolation for billions of years. This isn't just about science, it's about planetary stewardship. We have a moral obligation to explore other worlds as careful visitors, not as bulls in a cosmic china shop. To prevent this, spacecraft destined for sensitive locations like Europa undergo the most rigorous cleaning and sterilization protocols imaginable, a process that borders on science fiction itself. Every single component, from the largest solar panel to the tiniest screw, is meticulously assembled in ultra-clean rooms, environments with fiercely filtered air and engineers dressed head to toe in sterile bunny suits resembling something from a semiconductor factory. But clean isn't enough, it must be sterile. Components are baked at high temperatures for extended periods, a dry heat microbial reduction process that ensures any microbial life is cooked into oblivion. For parts that can't withstand such heat, like some electronics and sensors, technicians use chemical sterilants like vaporized hydrogen peroxide, which kills microbes without causing damage. The goal is to reduce the overall microbial load to astonishingly low levels, following strict international guidelines set by the Committee on Space Research. This entire painstaking process adds immense complexity, time, and cost to a mission, but it is considered non-negotiable. It is the price of conducting responsible, credible science beyond our planet. This concept extends beyond just protecting Europa from us. It also involves protecting Earth from any potential return samples. While a Europa lander is currently designed as a one-way trip, future missions conceptualize bringing a sample of ice or ocean water back to Earth for more detailed study in terrestrial laboratories. The protocols for such a return would be unprecedented in their caution. The sample return capsule would likely be intercepted in space and directed to a maximum containment facility, a biosafety level 4 lab with multiple layers of physical and biological isolation, similar to those used to study the most dangerous pathogens on Earth like the Ebola virus. The samples would be opened and analyzed inside sealed glove boxes, with the air filtered and incinerated before release, ensuring that not a single molecule from Europa could escape into our biosphere until we are absolutely certain it poses no threat. This isn't about fear of alien invasions, it's about prudent, careful science. We have no way of predicting how an extraterrestrial organism might interact with Earth's environment, and the precautionary principle must dominate our actions. Our desire for discovery must always be tempered by our duty to preserve, both for the integrity of other worlds and for the safety of our own. Determining the age of these cracks is crucial because if they are ancient and fossilized, they represent a historical record. But if they are fresh and actively forming, they change the entire game, suggesting that Europa is a world in flux right now, potentially offering us real-time access to its ocean. So how do we tell the age of a crack on a moon 500 million miles away? The answer lies in a technique astronomers have used for decades, counting craters. The fundamental principle is simple: the more craters a surface has, the older it is. In the solar system, impact craters are like wrinkles. They accumulate slowly over time. A surface that is smooth and nearly crater-free must be geologically young, as some recent process has erased the old, pockmarked terrain. When we apply this logic to Europa, the results are startling. Vast regions of its surface, particularly the complex networks of ridges and bands, show a remarkably low number of impact craters. In some of the most tectonically active areas, the crater count is nearly zero. This tells us that these features cannot be billions of years old. In fact, calculations based on the estimated rate of impacts in the Jovian system suggest that Europa's entire surface is, on average, only about 50 to 90 million years old. While that may sound ancient to us in geological terms, it's incredibly recent. To put that in perspective, the last dinosaurs walked the Earth around 66 million years ago. This means the entire surface of Europa has been completely repaved since the age of the dinosaurs ended. This constant renewal is the work of the very processes we've been discussing: the conveyor belt of plate tectonics, the upwelling of new material at cracks and bands, and the resurfacing events within chaos terrain. These forces are not relics of a bygone era. They are ongoing, actively scrubbing the surface clean of its cosmic blemishes, but the evidence goes beyond just a lack of craters. High-resolution images from spacecraft reveal stunning details within these cracks that scream of recent activity. We can see places where older geological features, like ancient ridges or even small craters, have been torn clean in half by a newer fracture. The edges of these cracks fit together like puzzle pieces, showing they have moved relative to each other, and the fracture line itself cuts across every older feature, proving it happened last. Perhaps the most compelling hint of all is the presence of what scientists call dark material. This is a mysterious, ruddy brown substance that appears to line the interiors of many fractures and coat some of the younger-looking terrain. Its exact composition is still debated, but it's likely a mixture of salts and organic compounds that have welled up from the ocean below. Crucially, this dark material appears to be relatively unstable on Europa's surface. Over time, it is probably eroded or altered by Jupiter's intense radiation, causing it to fade and lose its color. The fact that we see it so clearly, defining the sharp edges of the youngest cracks, indicates that it was deposited recently, and that the process that brought it to the surface is likely still happening. This isn't a frozen museum exhibit, it's a dynamic world where the art is still being created. We are not looking at a snapshot of the distant past. We are looking at a world that is alive, geologically speaking, right now. While Europa commands much of the spotlight in the search for life, it is far from the only intriguing ocean world in our solar system. To truly appreciate its potential, we must look across the void to another frozen moon orbiting a different giant planet, Saturn's brilliant, icy Enceladus. At first glance, they seem like cosmic twins, both small, ice-covered moons with subsurface oceans and spectacular geysers erupting into space. But a closer look reveals they are more like cousins, each offering a unique set of advantages and challenges for astrobiologists. This comparative planetology isn't just an academic exercise. It helps us refine our search strategies and understand which world might whisper its secrets first. The most striking similarity is, of course, the plumes. Both moons actively vent material from their hidden oceans, providing a free sample for any passing spacecraft. However, the nature of these eruptions is dramatically different. Enceladus puts on a far more reliable and vigorous show. Its plumes are a constant, towering fountain of water vapor and ice grains, erupting from prominent fissures known as the tiger stripes near its south pole. These jets are so massive and persistent that they create one of Saturn's rings, the E-ring, constantly feeding it with fresh particles. This makes Enceladus an incredibly easy target. The Cassini spacecraft didn't just detect these plumes from a distance. It flew directly through them multiple times, analyzing their composition in stunning detail. Europa's plumes, by contrast, are the definition of elusive. They are intermittent, harder to predict, and appear to be smaller and more diffuse. Catching one in the act has been a challenge, with observations from the Hubble Space Telescope providing tantalizing but not yet definitive evidence. This difference in reliability is a major practical factor for exploration. A mission to Enceladus is almost guaranteed a good sample. A mission to Europa might require more patience and luck to successfully fly through a plume at the right moment. When it comes to the oceans themselves, the moons differ in both their scale and their setting. Europa is a much larger world, and its ocean is correspondingly vast, a deep, global saltwater sea containing more than twice the water of all Earth's oceans, sealed under a thick, complex shell of ice. Enceladus is tiny, only about 310 miles across. Its ocean is not global but regional, a great sea trapped between its rocky core and its icy crust, likely concentrated around its south pole. This difference in size has profound implications. Europa's immense ocean has likely existed for billions of years, providing a potentially stable environment for life to originate and evolve over an immense timescale. The longevity of Enceladus's smaller ocean is a bigger question, as its energy source might be more variable. However, what Enceladus lacks in size, it may make up for in chemical enthusiasm. The data from Cassini's flights through the Enceladan plumes revealed a shockingly promising environment. The ice grains were found to be rich in sodium salts, indicating the ocean is salty and has been in contact with a rocky seabed. Most importantly, the plumes contained a variety of simple organic compounds, including methane, carbon dioxide, and propane. Most thrillingly, Cassini detected molecular hydrogen, a gas that, on Earth, serves as a potent fuel for microbes living around hydrothermal vents. This discovery points directly to active hydrothermal systems on the seafloor of Enceladus, where hot rocks are interacting with ocean water and providing the kind of chemical energy that could power life. We do not yet have this level of detailed chemical confirmation for Europa, though the Europa Clipper mission is designed to get it. Based on surface geology and magnetic field data, we strongly suspect a salty ocean and hydrothermal activity, but the proof will be in the plume sampling. Europa's potential advantage may lie in the sheer volume and stability of its ocean. A larger, older ocean might have allowed for more complex ecosystems to develop, perhaps even beyond the microbial stage. It's the difference between a potentially vast, ancient abyss and a smaller, but incredibly energetic hot spring. So, which world offers the better prospects for life? The answer isn't simple, and it depends on what we're looking for. Enceladus presents the clearer, more immediate opportunity for detection. Its plumes are a veritable fire hose of ocean material, easily accessible and already known to contain organics and a key energy source. A mission that could quite plausibly find evidence of life or the complex chemistry that precedes it within its first few fly-throughs. It is the low-hanging fruit of ocean world exploration. Europa, however, may represent the higher ceiling. Its ocean's immense size and ancient age suggest an environment that has had far more time and space for life to arise, diversify, and potentially achieve complexity. Finding life there might be a harder technical challenge, requiring a lander to drill into the ice, but the reward could be exponentially greater. We are not just looking for microbes, we might be looking for an entire hidden biosphere. The quest to understand these two magnificent worlds is not a race but a parallel journey. Together, they teach us that habitability is not a single formula, but a spectrum of possibilities, and our solar system is far richer and more wonderful than we ever dreamed. Yet for all the scientific precision and technological marvel, this quest is driven by something far more profound than mere curiosity. It is fueled by a deeply human yearning to answer one of our oldest and most fundamental questions: are we alone? Every culture throughout history has looked up at the stars and wondered if other eyes were looking back. That question has been the domain of poets, philosophers, and priests. But now, for the first time, we are building the tools that could transform that ancient speculation into empirical fact. Finding life on Europa would not just be a discovery, it would be a revolution, a paradigm shift in human thought that would ripple across every facet of our existence, from science and technology to philosophy, and even our own sense of identity. Scientifically, the implications are almost too vast to comprehend. Confirming a second, independent genesis of life in our own solar system would be the single greatest biological discovery in history. It would provide the first concrete data point in the equation for the Drake equation, moving us from guesswork to grounded estimation. It would tell us that the transition from chemistry to biology is not a miraculous, one in a trillion fluke unique to our planet, but a natural and perhaps even common process wherever the right conditions persist. Suddenly, the universe would feel biologically rich, teeming with potential. A microbe from Europa would become the most studied organism ever, its biochemistry a Rosetta Stone for understanding the universal principles of life. Does it use DNA and RNA, or a completely different molecule for heredity? Are its cells built with the same lipids and proteins? Every answer would either reveal a stunning convergence of life's architecture or open the door to a breathtaking new biology unlike anything we know. Beyond the laboratory, the philosophical and cultural tremors would be equally powerful. For centuries, our worldview has oscillated between two extremes: the anthropocentric view that humanity is the center and pinnacle of creation, and the Copernican principle that we occupy a random, insignificant speck in a vast and indifferent cosmos. Finding life next door on a moon of Jupiter would resolve this tension in a startling new way. It would decisively confirm that we are not the center of the universe, but it would also powerfully suggest that we are not alone in it. We would shift from being a solitary wonder to being part of a community, a single thread in a vast cosmic tapestry of life. This realization could fundamentally alter our perception of our place in the cosmos, fostering a new sense of cosmic kinship and perhaps even a greater responsibility to safeguard the fragile spark of life wherever we find it. This discovery would also force a profound reconciliation between science and spirituality. many of the world's religions and philosophical traditions would need to grapple with the existence of a second Genesis. Would life on Europa have a soul? Would it be part of a divine plan, or does its existence point to a universe where life is an emergent property of matter and energy, a natural outcome of cosmic evolution? These are not questions a mass spectrometer can answer, but they are questions that would be debated in churches, temples, universities, and dinner tables across the globe. The discovery would not necessarily negate faith. Instead, it could expand it, challenging us to develop a theology and a philosophy as vast and inclusive as the cosmos itself. Ultimately, the icy cracks of Europa are more than just geological features. They are a mirror. Staring into them, we are not just looking for aliens, we are looking for a reflection of ourselves, seeking to understand what it means to be alive in a universe of staggering scale and beauty. The journey to answer whether we are alone is, in its deepest sense, a journey to understand our own significance. It is the greatest story ever told, and we are all living in the chapter where we finally turn the page. The very same technologies we are pioneering to unveil the secrets of a distant moon are already beginning to pay remarkable dividends right here at home, transforming our ability to understand and protect our own planet. The monumental challenge of exploring Europa is acting as a powerful catalyst for innovation, forcing engineers and scientists to push the boundaries of the possible. In solving the extreme problems posed by an icy world millions of miles away, we are creating powerful new tools for Earth sciences, climate research, and the exploration of our own most remote and hostile environments. Consider the development of next-generation ice-penetrating radar systems. For missions like Europa Clipper, scientists couldn't just use off-the-shelf technology. They had to design radar instruments of unprecedented power and sensitivity, capable of seeing through 10 miles of alien ice and distinguishing between solid ice, slushy brine, and liquid water pockets. The algorithms developed to process this complex data and construct three-dimensional maps of the subsurface are marvels of computational geophysics. This technology is now being adapted for use in Greenland and Antarctica. The improved resolution and depth penetration allow glaciologists to map the bedrock beneath our ice sheets with far greater accuracy than ever before. This is not an academic exercise. It is critical for predicting how these massive ice sheets will respond to a warming climate. By understanding the topography hidden beneath the ice, we can better model how glaciers will flow and melt, leading to more accurate forecasts of global sea level rise. The quest to map Europa's ocean is directly helping us map the future of our own coastlines. Similarly, the problem of navigating and exploring a lightless ocean hidden under a thick ice ceiling has spurred incredible advances in robotics, particularly in the field of autonomous underwater vehicles, or a UVS. Engineers are designing cryobots, self-contained, heated probes that can melt their way vertically through miles of ice, and hydrobots, which will be deployed into the ocean below to explore autonomously. These robots cannot be controlled by joystick from Earth. The communication delay is far too long. They must be smart. They need artificial intelligence to navigate unknown terrain, avoid hazards, make independent decisions about where to sample, and prioritize their scientific objectives without human intervention. The autonomous navigation systems being developed for a potential Europa hydrobot are a quantum leap beyond current subsea drones. These advancements are already filtering down to oceanographers studying the Arctic and Antarctic. A UVS equipped with similar AI can now undertake longer, more complex and more dangerous missions under sea ice, collecting data on water temperature, salinity, and current patterns that are vital for climate models. They can map previously inaccessible regions, helping us understand how polar oceans are absorbing heat and carbon dioxide. Even the rigorous planetary protection protocols designed to prevent the contamination of Europa are leading to breakthroughs in sterilization and cleanroom technology. The methods developed to bake and chemically treat every component of a spacecraft to an almost unimaginable level of cleanliness have direct applications in industries where sterility is paramount, such as pharmaceuticals, semiconductor manufacturing, and medical implant production. The techniques for detecting infinitesimally tiny traces of biological contamination on spacecraft surfaces could lead to new, hypersensitive sensors for monitoring cleanrooms in hospitals or detecting pathogens in public spaces. The spin-offs are not always as dramatic as a new radar system, but they are a testament to how tackling the hardest problems in space exploration forces us to innovate in ways that often ripple out across our entire technological society. This two-way flow of knowledge and technology creates a powerful virtuous cycle. We develop a new tool to explore the extremes of our own world, which we then refine and harden for the ultimate challenge of space. Once proven in the unforgiving environment of deep space, that technology returns to Earth more capable and robust than before, ready to tackle the pressing problems we face at home. The ice of Europa and the ice of Earth are now linked by a shared quest for understanding, driven by tools born from our curiosity about other worlds. This demonstrates that the value of exploration is not just in the answers we find out there, but also in the new capabilities we build along the way. But our exploration cannot stop at the microscopic. The sheer scale and longevity of Europa's ocean forces us to ask a far more thrilling question. If simple life gained a foothold billions of years ago, could it have evolved into something more complex? Could there be ecosystems in that abyss with predators and prey in a world without a single ray of sunlight? This is not mere fantasy. It's a scientific speculation grounded in the principles of biology and energy availability. The primary constraint in any ecosystem is energy. On Earth's surface, the vast majority of food webs are built on the foundation of photosynthesis, harnessing the sun's abundant energy. Europa's deep ocean has no such luxury. All life there would have to be chemosynthetic, deriving energy from chemical reactions. This might seem like a severe limitation, but as we've seen around Earth's hydrothermal vents, chemosynthesis can support surprisingly dense and diverse communities. The critical factor is the flux of chemical energy. How much is consistently available? This is where Europa's stability might offer an incredible advantage. While individual hydrothermal vent fields on Earth are ephemeral, perhaps active for only decades or centuries, the tidal heating that powers Europa's geological activity is global and constant, likely sustained for billions of years. This suggests that its vents could be incredibly long-lived, providing a stable, persistent source of energy and nutrients not just for millennia but for eons. This timescale is crucial. Evolution operates through random mutation and natural selection, but it is fueled by time. The 4-billion-year history of life on Earth has allowed for the gradual accumulation of complexity, from the first simple cells to the astounding diversity we see today. Europa's ocean has potentially had a similar multi-billion-year timeline to work with. In an environment with stable energy sources and no major extinction-level events from asteroid impacts or solar fluctuations, evolution could have taken its time, patiently experimenting with different forms. So what might these more advanced organisms look like? We can make some educated guesses based on the environment's constraints. Vision, as we know it, would be useless in the perpetual, absolute darkness. Other senses would be paramount. Organisms would likely rely heavily on sensing vibrations through the water to detect movement, much like fish on Earth use their lateral line. They might also possess exquisite sensitivity to chemical gradients in the water, allowing them to smell prey, predators, or mates from great distances. In the absence of light, bioluminescence could be a widespread form of communication, used for attracting mates, luring prey, or even confusing predators. The water itself would be cold, just above freezing and under immense pressure. These conditions favor slower metabolisms and a more deliberate pace of life. We might not find fast-swimming, muscular predators like sharks, but perhaps something more akin to a giant, slow-moving cephalopod or a delicate, frilled filter feeder that drifts through the water column, harvesting snow like organic detritus falling from the ice shell above. Body plans would be shaped by the need to conserve energy. Streamlined shapes for efficient movement would be beneficial for any mobile creature. Buoyancy would be a constant concern. Without a swim bladder filled with air, organisms might use pockets of lighter gases or fatty tissues to maintain their position in the water column, or simply remain largely sedentary, attached to the rocky seafloor near nutrient-rich vents. The most complex ecosystem might revolve around these hydrothermal vents, forming a food web similar to Earth's. Microbial mats would form the base, fed by the vent's chemicals. These mats would be grazed upon by small, snail-like or shrimp-like creatures. These grazers would, in turn, be prey for larger mobile predators. The top predator in this dark world might be a sleek, efficient hunter, using a combination of vibration sensing and chemoreception to track its meals, perhaps even capable of a stunning burst of speed for a final, decisive strike. While finding intelligent, technological life like our own is incredibly unlikely, the environment lacks the selective pressures for manipulating tools or creating fire. Finding a world teeming with complex, multicellular animals is a distinct and breathtaking possibility. Europa's ocean may not hold cities, but it could very well hold forests of strange tubeworms and schools of alien fish, a testament to life's relentless creativity in the most unexpected of places. This global endeavor to understand Europa is not the work of a single nation or agency. It is a testament to the power of international collaboration in the face of a monumental scientific challenge. The sheer complexity and cost of exploring a world so far away, hidden under ice and bathed in radiation, demands a united front. No single space agency possesses all the resources, expertise, or funding to tackle this alone. Instead, we are witnessing an unprecedented level of cooperation, where NASA, the European Space Agency, and other partners are pooling their strengths, sharing the immense burden, and ensuring that the scientific return from these missions is greater than the sum of its parts. This isn't a race to be first, it's a shared journey of discovery where success is measured by what we learn together. At the forefront of this collaborative spirit are two flagship missions, perfectly designed to complement each other. NASA Europa Clipper is the dedicated reconnaissance orbiter, built to conduct detailed surveillance of the Moon and identify the most promising locations for a future lander. Meanwhile, the European Space Agency's Jupiter Icy Moons Explorer, or JUICE, has a broader mandate to study the entire Jovian system, with a significant focus on Ganymede and Callisto as well as Europa. While their primary objectives differ, their paths and data will intertwine in powerful ways. JUICE arrived at Jupiter first, providing a wealth of contextual data on the radiation environment, the magnetic fields, and initial observations of Europa that will help inform and optimize Clipper's more intensive survey when it arrives. This sequential partnership means that by the time Clipper begins its close flybys, mission scientists will already have a richer understanding of the playing field, allowing them to fine-tune their observations from day one. The collaboration extends far beyond mere timing. It is woven into the very hardware of the missions. JUICE carries a vital US-provided instrument, the Radar for Icy Moon Exploration, or RIME, an ice-penetrating radar essential for peering beneath the surfaces of its targets. In return, European institutions contributed key components to several of Clipper's instruments. This cross-pollination of technology ensures that both missions benefit from the best expertise available on the planet, regardless of national borders. It also mitigates risk. If a particular technology or component faces development challenges in one country, partners elsewhere can often step in with a solution, ensuring that the entire mission isn't held back. This shared investment in hardware creates a powerful mutual interest in the success of both spacecraft, fostering a true spirit of partnership among the engineering and science teams. Perhaps the most profound collaboration happens after the data starts streaming back to Earth. The science teams for Clipper and JUICE are deeply international, with researchers from across the globe working side by side to calibrate instruments, interpret findings, and build coherent models of these alien worlds. They operate under data sharing agreements that prioritize open access, meaning a scientist in Japan or India can work with the same dataset as a researcher at the Jet Propulsion Laboratory or the European Space Research and Technology Center. This global brain trust is essential for tackling a puzzle as complex as Europa. A geologist might see a pattern in the surface fractures that a radiation specialist can then correlate with their data, while a chemist interprets the spectroscopic signatures of the dark material lining those cracks. It is through this constant cross-disciplinary dialogue that the biggest breakthroughs will emerge. This model of international partnership, perfected through decades of cooperation on projects like the International Space Station, is now being applied to planetary science with spectacular ambition. By sharing the financial costs and the technological risks, these agencies are able to pursue missions that would be too expensive or too complex for any one of them to attempt alone. More importantly, they are building a framework for the next logical step, a potential Europa lander. The technological and planetary protection challenges of landing on Europa are so immense that they will undoubtedly require a global effort. The collaborations being forged today on Clipper and JUICE are laying the essential groundwork for that future mission, proving that when humanity sets its sights on understanding the universe, our greatest asset is our ability to work together. While orbiters and landers can provide incredible insights, the ultimate dream remains sending a probe directly into Europa's ocean to see it with its own eyes. This ambition pushes our engineering to its absolute limits, demanding a vehicle that can perform the most audacious tunneling operation in history. The concept at the forefront is the Cryobot, a nuclear-powered, self-contained melting probe designed to slowly and steadily descend through the ice by turning it into water. Picture a sleek, cylindrical vehicle, perhaps several meters long, with a heavily shielded radioisotope thermoelectric generator at its core. This RTG provides a constant, reliable source of heat, not for propulsion, but for a simple yet brilliant process. At the tip of the probe, a hot plate heated by the RTG presses against the ice. The intense heat melts the frozen water directly in front of it, and the probe, pulled by its own weight, gradually sinks into the newly formed meltwater. This journey would be a slow, solitary descent into darkness, taking weeks or even months to traverse the 10 to 15 miles of ice. The meltwater created by the probe doesn't simply disappear. It flows around the sides of the vehicle and refreezes behind it, sealing the probe into a perfect, isolated tunnel. This is a critical feature for planetary protection, as it ensures no Earth microbes clinging to the probe's exterior could contaminate the pristine ice on the way down. The Cryobot wouldn't just be a passive melter, it would be a fully equipped scientific laboratory analyzing the ice it passes through in real time. Its sides would be studded with instruments' miniature mass spectrometers to identify complex organic molecules, microscopes to search for cellular structures, and sensors to measure the temperature, pressure, and chemical composition of the surrounding ice. This descent would provide the first vertical profile of Europa's crust, revealing its layered history, identifying pockets of brine, and perhaps even finding life frozen within the ice itself long before it ever reached the ocean. The moment of breakthrough would be one of the most dramatic in the history of exploration. After its long descent, the Cryobot would finally melt through the final layer of ice and emerge into the open water of the global ocean. At that instant, it would transform. A secondary module, the Hydrobot, would likely detach from the melting unit. This free-swimming, autonomous underwater vehicle would be the first explorer of an alien sea, a robotic ambassador swimming into the eternal night. Its design would draw heavily from our most advanced Earth-based submersibles, but it would need to be entirely autonomous. With a communication delay of over 40 minutes each way, no one on Earth could joystick it around obstacles. It would rely on sophisticated artificial intelligence to navigate, map its surroundings with sonar, avoid hazards, and make critical decisions about what to sample and analyze. The Hydrobot's sensor suite would be its eyes, ears, and nose in the abyss. High-resolution cameras with their own powerful lights would capture the first-ever images of this hidden world. A mass spectrometer would continuously sniff the water, hunting for the chemical signatures of biological activity. It might carry a suction sampler to pull water and any suspended particles into a containment cell for more detailed analysis, and a robotic arm to collect solid samples from the seafloor or from the underside of the ice ceiling. Its most exciting mission would be to seek out the sources of energy that could power life, to find a hydrothermal vent field on the seafloor. Guided by sensors that detect subtle changes in water temperature and chemistry, the Hydrobot would follow a chemical plume to its origin, potentially arriving at a landscape as alien and awe-inspiring as anything ever imagined, where the possibility of encountering life in the waters of another world becomes breathtakingly real. So as we've journeyed from the chaotic surface ridges down to the potentially life-rich hydrothermal vents on the ocean floor, a powerful picture comes into focus. Europa isn't just a frozen statue in the void. It's a dynamic, breathing world where the very cracks scarring its face are not scars at all, but vital arteries. These fractures, driven by Jupiter's immense gravitational pull, may be the critical conduits that connect the lethal, radiation-bathed surface to the protected, nutrient-rich ocean below. They could be facilitating a constant, slow-motion exchange, delivering chemical energy manufactured at the surface by radiation down into the depths, while occasionally allowing a sample of the ocean to well up and freeze for us to find. This ongoing geological activity transforms Europa from a static object of study into a living system, one that might be actively fostering and sustaining biology in its dark global sea. This combination of ingredients, a vast liquid water ocean, likely hydrothermal energy from below, and these potential pathways for nutrient exchange, is what places Europa at the very top of the list in our search for life elsewhere. It presents a more compelling and complete astrobiological package than almost any other world we know. The upcoming missions, from the orbital reconnaissance of Europa Clipper to the future dream of a lander or even a cryobot, are designed to follow these pathways, to read the story written in the ice and finally answer the question of whether we share the cosmos with another genesis of life. The next decade will bring us data that could fundamentally reshape our understanding of our place in the universe. I encourage you to follow along as these discoveries unfold. Subscribe for updates on these missions, and let me know in the comments what you think we'll find. Do you believe those dark, jagged cracks are the signs of a world teeming with life, or will Europa's ocean be a beautiful but sterile abyss? The greatest discovery in human history might be waiting for us, not around a distant star but right next door, orbiting a giant